Now, in addition to the second order method to solve beam deflection problems, there also exists a fourth order method, which eventually you will see it reduces to the second order method itself. Now, this fourth order method that you see that is particularly useful when you are solving for beams which has a uniformly distributed load. And the reason why it is useful is that we will see in a minute that if you take the fourth order derivative of your deflection, that becomes equals to the load. And let's see that how does that happen. But as I said, that the fourth order method, once you start to integrate that, if you integrate it twice, you end up with d square y by dx square, which eventually boils down to the second order method. So if you have, say, beams, for example, here with a uniformly distributed load and so on, and we know that with this relationships we had studied from our, when we were looking at the chapter on shear force diagrams and bending moment diagrams, that our dm dx is equal to your shear, the derivative of the moment is equals to the shear, and the double derivative of the moment equals to dv dx equals to minus w of x. Remember, w is acting vertically down over here, that's why you get the negative sign. So this relationship, as you see, and let me maybe mark that explicitly over here, that where we have studied this from. So this we have studied from our SFD BMD chapter, right? So if you go from this one over here, now you know that one relationship that we have, that our EI with d square y by dx square equals to m, which we have seen already in the second order method. So what did we see in the second order method? That our, if you recall, that our EI d square y dx square equals to m. Now, if you take the double derivative of that one again, you end up with EI d4y by dx4, which becomes equals to, you would have to take the double derivative of this one, which is this guy over here. And from these two, the first two bullet points that you see, these two guys, you can write this one as simply equals to this one over here, and which you see over here equals to minus w times x. So essentially now you have a relationship between the fourth order derivative of the deflection and the distributed load that is over here. So it all follows from this interrelationships between the moment and the shear and the load. So now from here, how do we get the value of w? You're right, you have to integrate this 4 times. So now since you're integrating it 4 times, you will have 4 constants of integration to deal with. So if you integrate 4 times, you essentially get something like this, and you get 4 constants of integration: c1, c2, c3 and c4. And how do we determine these constants, these 4 constants of integration? Again, from the boundary conditions we look at, right? So we'll look at a short example problem, and as I said, you will see that in that one, the fourth order method, when you integrate it 2 times, you end up with the second order method. So you can just start the problem with the second order method itself if you want to do it, but just for the sake of demonstration, let's do a problem where we start with the fourth order method and boil down to the second order method and eventually find the deflection of the beam. In this example problem that you see, you have a beam with a uniformly distributed load W, a beam of length L, which is supported by a pin support and a roller support at the other. In one of the problems before, I had asked you to try solving this beam using the second order method, and I hope you have got the answer that we looked at. Now, if we try to solve this using the fourth order method that we have over here, we can write the basic equation to start with as EI. Now in this case, since W is a constant, I can simply write it as equals to W over here. Now if you integrate it 2 times, you will get d square y dx square, and you will introduce 2 constants of integration. So let me just go ahead and write that. Now remember, here we have now introduced 2 constants of integration, c1 and c2, and if you recall that EI d square y by dx square is nothing but equals to the moment m. So this guy is nothing but equals to m of x. So before integrating it 2 times again to get the y, we can solve for c1 and c2 here directly. And how can we do that? See, this is a simply supported beam over here where we know at the left end, that is at x equals to 0, I have the moment as equals to 0 because it's a pin support, and at x equals to L also the moment equals to 0 because it's a roller support over here. So if you substitute those things over here, that is at x equals to 0, your this entire quantity is 0 because the moment is 0 over here, and also at x equals to L, this entire quantity is 0 because moment equals to 0. So that will give you C1 and C2. So let's go ahead and do that. So now that we have evaluated these two constants, C1 and C2, we can go back and plug that in this equation over here. So now we'll have EI d square y by dx square equals to minus wx square by 2 plus wlx by 2 plus 0. So let's go ahead and write that. So had you started this problem using the second order method itself, as I had asked you to do, then you'll begin your problem with this equation. This, remember, is nothing but at any section x, if you take the moment, that comes out as something like this over here. The rest of the problem is more or less the same, that you integrate it 2 times again. So you get 2 more constants, say C3 and C4. Then you use the other 2 boundary conditions, that at x equals to 0, y equals to 0, at x equals to L also y equals to 0. So let's go ahead and plug those things and let's see what we get as a C3 and C4. So you will get your C3 as minus WL cube by 24, and you will get C4 as 0. So if you plug this guy back over here, then in that case you will get your the equation of the elastic curve. So let's go ahead and plug that and get the equation for elastic curve. Now from this equation, see, the problem asks you the equation of the elastic curve, which we have gotten here already, and the maximum deflection. Now you can do dy dx equals to 0 and find the location. It is very obvious here that the maximum deflection is going to happen at L over 2, and the magnitude of the maximum deflection is going to be So this is the estimate of the maximum deflection that you get. So you saw, I hope you understood this problem, that how we from the 4th order method we integrated it twice and you got the 2nd order method, and after that the rest follows how we did before, that you integrate it twice again, and in all the steps you determine the constants of integration using your boundary condition.